Hello everyone, welcome to the course on computer aided drug design. We have been talking about numerical methods for finding out differentials. Now we will look at numerical methods for solving differential equation. Okay, numerical methods is a course by itself, so I am just going to take 1 or 2 lectures on this topic, okay, just as a prelude to the entire concept of numerical methods, because they are used when you talk about minimum energy conformation and so on actually. Okay, so we were talking about numerical differentiation, that means estimating the derivative of a mathematical function. It is called a finite difference approximation based on 2-point estimation. So if you have dy by dx, as you know, it can be approximated as delta y by delta x, which is delta y is y at x plus h minus y at x divided by h. Okay, so basically y at x plus h will be here and y at x will be here. Okay, so you take this difference and you divide by h. Okay, that gives you the dy by dx. As you know, dy by dx is the slope. Actually you would like to do it here, okay, whereas you take the much bigger region. So if the h is small, then you are approximating or to the exact slope at this point of place at x. Okay, that is how it is. So smaller the h, more accurate is your answer. Larger the h, as you can see in this figure, you are not reaching the correct answer. Okay, so dy by dx, as this becomes the dy by dx, delta y by delta x becomes dy by dx only when h becomes smaller and smaller and smaller actually, okay, tending to 0. So there are as I said, this normal simple method for 2-point method which calculates the dy by dx as you go along the slope. The error in this particular case is in the order of h square, so which could be very high, and yesterday I showed you an example of this, how much the h change depending upon h. If h is 0.001, you may get 0.1% error. If h is 0.01, you may get 1% error. If h is 0.1, you may get 10% error, depending upon how the equation is, because if you have a parabolic type of a relationship, errors could be much larger. There are higher order methods also which can do a better job of estimating dy by dx. Here the error is of the order of h raised to the power 4. Okay, so that is quite small. The higher order methods is, as I showed you here, you have estimate the y at x plus 2h, estimate the y at x minus 2h, then estimate the y at x plus h, x minus h, and then use different coefficients as shown here, okay, divided by 12h, and you get the dy by dx. Okay, so depending upon where you estimate, these coefficients can change. In fact, this particular website gives you the values of the coefficient. Okay, for example, let us have a look at it actually. Yeah, so if those 5 points are at minus 2, minus 1, then at plus 2, plus 1, okay, this is how the equation will look like I showed you here, okay, fx minus h, okay, like I showed you here. So we have 8, 8, minus 1, plus 1. So we can change these sample points and you will end up with the different coefficients. For example, if I change it to 2, 1, 0, 1, 2, okay, so you see this is how it will look like. So it is estimated at 0, it is estimated at plus h, plus 2h, and the coefficients are minus 3, plus 4, and minus 1. Okay, so depending upon which are the 4 points you plan to do, oh sorry, minus 1 0 plus 1 oh shit 2. Okay, so it gives you different sets of coefficients here, as you can see here. Okay, so depending upon which points we want to use, it gives you different sets of equations and different coefficient values, as you can see. For x plus 3h, x plus 2h, x plus h, because this is what we have written 3 2 1, and this is x plus 0, that is at x itself, and then minus 1. So we have different sets of coefficients here. Okay, so depending upon how you want to estimate your dy by dx, which 5 points you plan to use, then it changes accordingly. Okay. As you can see here. Okay, so here I have taken only 4 points, minus 2, minus 1, 0, 1. Okay, so it is not really symmetric on both sides of 0. So you have different sets of coefficients here, and the denominator also is very different as against this. Here we are considering symmetric, plus 2h, minus 2h, plus h, minus h. Okay, whereas here we are taking minus 2, minus 1, 0 and 1 here. Okay, so you have different sets of coefficients here. Okay, so this is a very useful okay, website where we can get the coefficients depending upon how we are going to use the sampling points. Okay, so now how do we solve differential equations? Suppose I have dy by dx is equal to fxy. Okay, so y at n is known. I want to find out y at n plus h, y at n plus 3h, 2h, 3h, 4h, like that. Okay, this is called the numerical integration or solving differential equations. Okay, this is also very useful because we want to differentiate and then calculate y at different values of x. The x could be time, especially if you are doing a molecular dynamics study, and as time changes you want to know how the coordinates change of the molecule. Okay, so you may have differential equations and you may calculate as a function of time at t equal to t0, t equal to t0 plus h, t0 plus 2h, like that. You want to find out the coordinates. Okay, so in such situations you will be solving differential equation. Okay, so the simplest method is the Eulers forward method. Okay, so what it does is just like the original we looked at long time back in this okay, this one we use the similar one. So yx plus h, so you can put this on this back, so you get yx plus h. So on same way here also yn plus 1 is equal to yn plus h f xn yn. Okay, so if I know the value of y at a certain time point, okay, if I want to find out at the next time point plus h time point, then I do yn plus h into f xn yn. Okay, so for example you are here xn yn, this is xn yn, and you want to find out what will be the yn plus 1. Okay, what will be the yn plus 1 at this particular time point. So what do? You do like this, yn plus, okay, so you do yn plus h f xn yn. Okay, so this is the function which you have to substitute here actually. Then the next time point you go. So depending upon how large is your step length, okay, how large is your step length, the error also goes down. Okay, just like the other which I showed you, the numerical okay, differentiation. And so smaller the step length, more accurate will be the answer. As you can see, when you have very quadratic or very sharp changing graphs, you are going to have problem in estimating the yn plus 1 starting from yn. Okay, again there are many different methods here, but Euler's method is the easiest one. And so if there is a sharp change, unless the h is very small, okay, so for example if your xn plus 1 is here, then xn plus 1 is here, that means h is very small, you will get a very accurate answer here, as you can see here. But if your h is large, as you can see here, there is a lot of error in estimating yn plus 1. This is the actual, whereas this is what the numerical method will tell you. So smaller the h, more accurate you can go along this graph. So we can have small h, then that way you will go along this graph. Larger the h, you may end up with this type of graph here. Okay. So the step length makes a lot of difference, and the error in estimation of yn plus 1. Okay, smaller the step. Okay, for example, let us look at this dy by dx is equal to y square. Okay, I want to calculate at some other next time point and so on. So this can be done. So if you want to solve, for example, an equation like this, dy by dx is equal to say y square. Okay, imagine this is x and this is y. Okay, x we may put it as say 2, then we can say put it as the step length can be 0.01. So this can be so you want to calculate. So like I mentioned, yn plus 1 is equal to yn plus h multiplied by the function. Okay, so how do you do that? So we will take this is equal to this plus the h step length, okay, multiplied by the y square. That means we take this raised to the power 2. Okay, so it's 2.04 at this at 2.01. Okay, and so on actually. So we can calculate each step, and B4 into $B2 plus B4 square. So then we can calculate. Okay, so as you can see, it keeps y keeps increasing. Okay, so suppose if the step length is okay, so as you can see, it's rising very drastically, the y value, if the step length is very large, whereas if the step length is very small, it will not rise so drastically. 0.01. Okay, as you can see here. You can also check out what is the actual value. So if the step length is very, very small, So, the rise is small, so it is much more accurate, whereas if I put a larger step length, as you can see here, okay, it rises very fast and the system can become very unstable. Okay. So, these type of methods you need to have a very small step length. So, the number of calculations keep increasing if you have smaller step length. So, there are other methods are all there which can give a better accuracy. Okay. That is the, it is very simple, as you can see, it just takes the h, multiplies by the y value, I mean the function value, that is dy by dx value, adds it up to the y starting y. So, it calculates y n plus 1, and as I said, if the step length is smaller, okay, you are going to have following slowly with this curve, whereas the step length is very large, then you will take large steps. So, you can see the error in this case, actually quite large error actually. But as I said, there are many other methods which are more accurate. We will look at them little bit, which gives values so that it follows the curve. So, if I have a larger step length, like I showed you in the Excel, suppose this is the true value, this is the true value. Okay, if I have larger step lengths, okay, especially for an equation like this 1 minus e power minus at, 0.25 step length, as you can see, it is deviated. If I have taken 0.5 as my step length, you can see it is deviated much more. These problems will arise when you have quadratic terms, quartic terms, exponential terms, and as you know, in our force fields we come across quadratic, quartic and exponential terms for most field. So, you will find large variations if you have large step length. So, this is the effect of step length. Okay, so as I showed you, if the step length is very large, that is the x axis, the actual value, if this is the actual value, you may be going like this actually, like I showed you in this example, right. You may be going like this, whereas the actual graph is like this. Okay. Okay, so when we have very small step length, we should be going along this graph. Okay, then there is another method that is called a trapezoidal method. Okay, this method is slightly more accurate. So, what you do is yn plus 1 is equal to yn h fx n yn. Okay, then you also calculate fxn plus 1 yn plus 1, and you calculate fxn yn, and then you take half of that. That means you take average of these two slopes. Okay, one slope which comes here and one slope which comes here, and then you take the average. That is what this particular term is all about actually. So, by doing that you get better accuracy. So, you look at this Eulers method. Okay, you take the slope only at this place. Okay, only at this place. Whereas in this method, in Heinz method or trapezoidal rule method, you take at these two places and then you take an average. That is how you calculate yn plus 1. So, how do you get this is the first approximation for yn plus 1, and then you substitute in your equation and then you take the average. Okay, so that method gives you a better answer. Okay, so as you can see, this is like predicted for yn plus 1. This is like your original Eulers method, but you do not stop there. You put that into the function. Okay, so get the function, and then you take the average of the functions, the xn yn, xn plus 1 yn. So, this is corrector, this is predictor. We call this as predictor. Okay, this is a predictor equation which is like your Eulers method. But you are improving on the yn plus 1 by having another equation we will call is corrector. Okay. This is the trapezoidal method as such. Okay. Then we also have the backward Eulers method. We have the backward Eulers method, just like backward differentiation method. Okay. So, as you can see dy by dx is equal to yx minus yx minus h. Okay, so instead of you taking x plus h, you are taking yx minus h, and then you calculate yn plus 1 is equal to. So, you take the differential from the previous and then use that for your yn plus 1. Okay. As I said, this is the method, Eulers method. Then we have the trapezoidal method, which takes an average of slope at xn yn and xn plus 1 yn. And then so if you look at Eulers method, simple, least accurate, this is a first order method. Then we also have the midpoint method, where you take okay, at the middle point derivative used for the full width calculation, which is slightly more accurate. Okay, then we looked at backward Eulers method. Then we have second order Runge-Kutta method. This is the midpoint method, okay, that is midpoint here, which you make use of to calculate the yn plus 1. So, if you want to solve dy by dx is equal to fxy, the initial condition is yx naught is equal to y naught. Okay, so we have the step length. So, first calculate k1, which is h into f xn yn, that is at the starting point. Then you calculate k2 at the midpoint, h by 2. Okay, so xn at h by 2, yn at k1 by 2, and then make use of to calculate yn plus 1. So, yn plus 1 is equal to yn plus k2. So, here the error is of the order of h raised to the power 3. Okay. So, this is called the midpoint method. As you can see, you calculate the slope at xn plus h by 2, yn plus k1 by 2 here, as you can see here k1 by 2, and then make use of to calculate yn plus 1 value. Okay, that is called take a trial step, okay, here, and then determine for here, that is called the midpoint method. So, this is called a second order Runge-Kutta method, and error is of the order of h cube, okay, which is good. Then we have fourth order Runge-Kutta method. The error is of the order of h raised to the power 5. Okay. So, here we do lot of midpoint corrections. As you can see, you have k1 h f xn yn, k2 xn plus h by 2 yn plus k1 by 2. Okay. Again you calculate k3, making use of the k2 here, yn plus k2 by 3, and then you calculate k4. Okay. And then yn plus 1 is calculated like this, you know, k1 by 6, k2 divided by 3, k3 divided by 3, k4 divided by 6. So, you calculate the slope at many places, okay, 1, 2, 3, 4, that is why it is called fourth order Runge-Kutta method. But the errors is dramatically decreased, h raised to the power 5, okay. Whereas if you look at starting from your Eulers method, then going to your trapezoidal rule, then going to second order Runge-Kutta method, then going to fourth order Runge-Kutta method, the error keeps coming down from h square, h cube, h raised to the power 5. But the number of calculations increase, but the h step can be dramatically decreased, okay, so that we can do the calculations, I mean we can do the solving, numerical solving much faster. Okay. So, there are many more methods, which let us not spend too much time on these methods, because as I said, this is not a course on numerical methods, but this is meant to give you a flavor of the numerical differentiation, numerical solving of ordinary differential equation, and so on actually. So, the second order Runge-Kutta method, accuracy proportional h square, fourth order Runge-Kutta method give accuracy that is proportional to h power 4. Okay. So, this is a nice comparative picture. Okay, this is a nice. So, the this is the true solution, the dark continuous line. Eulers method you can see here, big one. This is Heinz method, sorry. Okay, this is the Heinz method, the Runge-Kutta method, which is following very closely. This is the Heinz method, and this is the Eulers method. you are using h is equal to 0.5. So, for this particular equation 1 minus e power minus at equation. Okay, then we have predictor corrector methods, Milne's method. This is called Milne's method. So, initially you predict for yn plus 1 and then you correct for yn plus 1. Okay. So, we calculate at 3 different places n minus 1, n minus 2, okay, and then we calculate yn plus 1, that is called a predicted for yn plus 1, and then again make use of that yn plus 1 to get corrected yn plus 1. This is called the Milne's method. Then we have the Adam-Bashforth-Moulton method. So, there are so many different methods. We will not go, as I said, into this Adam-Bashforth method. So, as you can see, Runge-Kutta method, Adam-Bashforth, Hans method, these are methods used in MATLAB, different types of methods. Okay. The computational time, you can see 0.05 seconds, 0.03 seconds, 0.03 seconds, and so on. Relative error, you can see 0.09. Adam-Bashforth gives 0.02 raised to the power 10 power minus 4. Okay, Hans method 0.0179. Okay, then ODE 23, 2045, 113, they all give these type of errors. So, you see, depending upon the method you use, we can get different levels of errors, and we can get different levels of computational time. Okay, it changes dramatically. As you can see, 0.09 to 0.01, so almost 8 times less error when you use different types of methods. Okay, so if you are looking at molecular dynamics, you want to see how the atoms change as a function of time when you have certain forces acting on it. So, if you are looking at atoms and you want to see atom motion, generally we are talking time step in the order of 10 power minus 14 seconds. Wow. If you have rigid molecules, you are looking at translation and rotation, then you should go 5 into 10 power minus 15, still smaller step. If you are looking at flexible molecules, rigid bonds, translation, rotation, torsion, so you need to have time steps 2 into 10 power minus 15. If you are having flexible molecules, flexible bonds, so you want translation, rotation, torsion, vibration, so you go 10 power minus 15, you go almost to 10 power minus 16 time steps, very small time steps. So, the number of calculations, so if you are integrating for 1 second, you need to do 10 power raised to the power 16 calculations, that is a huge set of calculations. So, that is why there is a lot of research that is being done to improve the integration. That means so that we can increase the time step, but at the same time keep our errors very, very small. Okay. So, if you are looking at translation, rotation, if this is your time step you are talking about, so the number of calculations are going to be very, very large. So, normally when we do a molecular dynamics study, we do not go to seconds or milliseconds, we stop much lower, picoseconds, because total number of steps are going to be very large. And especially if you are talking flexible molecules, you are looking at translation, rotation, torsion, so number of calculations are going to be very large. So, with that we will stop and we will continue more on this force field or molecular mechanics in the next class as well. Thank you very much for your time.